name is Dan Carnevale. I'm the director of Eaton's Experience Centers here in Pittsburgh and in Houston, Texas. And I welcome you today to this session. This is on basically rules of thumb and calculations that you'd like to know for doing consulting work in the power systems field. So we're going to talk about transformer calculations, fault current calculations, and so forth. So the purpose and learning of this event or this session is really to gain a good understanding of the key power system concepts and calculations that apply, and basically around rules of thumb. So if you're thinking about the person sitting next to you that's been in their job for a long time, we want you to understand how do they come up with these calculations. At the end of this presentation, you'll be able to size transformers, cables, and protective devices based on the three-phase calculations. And also to be able to understand the calculations for motor starting, power factor correction, and three-phase power. Engineers love to write on things. Pick a napkin, maybe at the back of an envelope, as people always say. Or one night when I was sitting at my kitchen table with my son, who's in engineering school, we were writing on the back of a pizza box. And it reminded me of the fact that engineers love to draw and love to do these calculations to think things through. And so to me, having the capability to come up with those numbers on the fly is important. And as an engineer, you need to understand where those equations come from and how to use them quickly and correctly to get you the right answers. In this session, we'll talk about three-phase calculations. So we're going to simplify it to those calculations that are appropriate for three-phase. There will be one or two that are single-phase, but we'll talk about those when they come along. The one thing that's important is really kVA. That's the main equation that we're going to use from the simple calculations of kVA, including voltage and current, and the square root of 3 were appropriate. We're going to talk about full load amps. How do you size the circuit breaker that comes into a transformer, or goes out of a transformer, or goes into a panel board or switchboard? And then how do we calculate fault current? And where do we calculate fault current? Breaker sizes and Ka ratings for that fault current. And then motor starting and load calculations. The power triangle, one of my favorite things to talk about. Kilowatts, kVAR, and kVA. And then power factor correction, and how do we use a one-line diagram to get all that information and put it together. Okay, so when do we use the square root of 3, the square root of 2, or the square root of 1? The square root of 3 is when we have three-phase calculations. Now, most people think that volts times amps equals watts, and we know that that's not true in AC power systems. Volts times amps equals volt amps, or kV times amps equals kVA. So when we have single phase power, we say kV line to neutral times I line equals VA, kVA single phase. If we multiply that by 3, we get the three-phase equivalent for a balanced system. Now, the square root of 3 comes into play when we have kV line to line, because kV line to line versus kV line to neutral is off by the square root of 3. kV line to neutral times the square root of 3 is the same as kV line to line. So when we have our typical three-phase power calculation, we're going to say kVA three-phase equals the square root of 3 times kVA line to line times the current. And that's going to be the equation that we're going to use a lot for the rest of the calculations for our transformers. When does the square root of 2 come into play? That really comes into play when we're talking about the RMS versus peak. Now, if you look at the peak and you compare that to the RMS, which is more of an average value, it's typically off by the square root of 2 when you have a very nice sinusoidal waveform. Where that doesn't happen is when you have harmonics, like the bottom picture, where the current has a crest factor or a peak over the square root of, or a peak over the RMS of maybe 3, or a number considerably higher than the square root of 2. So the square root of 2 comes into play for those kind of things, and as a consultant, you might not run into that as much unless you're dealing with waveforms and harmonics and things like that. But the square root of 3 will be all around, and if you understand those equations on the left, that's going to be a big deal if you can understand the square root of 3. Square root of 1 you can use for everything else. So as a consultant, why do you need a one-line diagram like this one? Well, it's really important. If you're going to try to do calculations, you really need to have a good understanding of the actual numbers of values for the equipment. And there's two things associated with that that are important. One is you don't always immediately trust a one line. You have to make sure that it's accurate. But the second thing is really to make sure that you have all the data that's on the one line that matches up with your equipment. So sometimes you have to field verify, again, through nameplates on equipment and so forth. But if we have the one line, like in this case, we can calculate and we can use the utility source impedance, the utility main breaker, substation transformer, um, medium voltage switchgear, like we show in the middle, unit substation transformer, for example, and then low voltage switchgear or switchboards, then multi-case breakers and dry type transformers down through the system. So all of that equipment with its proper information on the one line is going to be super helpful to doing your fault analysis and your load flow calculations and all of the things you'll do as an engineer or consultant. Now what we're going to do is we're actually going to go through and calculate full load amps on the primary and secondary of a transformer, the fault current on the secondary, and also the breaker or fuse size and the KA rating of those breakers. We're going to talk about how that comes into play here. Now, I'm going to actually take you for a walk and show you a couple of these transformers so you can physically see what they look like, because they're not just squiggly lines on a piece of paper. They're actually physical devices. And I'll show you the difference between the liquid-filled ones and the dry types and the pole-mounted ones and the things you're going to have in your one-line diagrams that won't necessarily correspond to something physical you've seen before. And I think that's really important to see how that all comes together.
So to get to the calculations that we need for a transformer like this, we want to think about full load amps on the primary, full load amps on the secondary, breaker sizing for primary and secondary, and then also fault current on the secondary. How are we going to get that information? Well, what we're going to do is we're going to go up to the nameplates of these transformers and we're going to find out the information that we're going to need to plug into our equations to calculate those values. Let's take a look at some actual transformers and see the ones that we're going to use in our calculations. This is the first one. This is a dry type transformer, 75 kVA, 480 volts in, 208 120 out, and it happens to be a K13 transformer, delta Y. So this next transformer is a little bit unique. We call it an isolation transformer, and what does that mean? That means the voltage on the input and output are the same, so we're just using it to reestablish a ground system through the delta Y and the Y connection on the secondary. This one happens to be 460 in, 460 out, 550 kVA. It's also connected, in this case not solidly grounded, but to our high resistance ground system, which allows us to have one free ground fault, and you might use that on an industrial situation, for example. Now here's a transformer on a pole. We can see it's single phase. It's 13,800 volts on the input and 240 120 coming into your house in the output. How are you going to figure out what size that one is? Well, we can see the 10 on there. What that means is 10 kVA. But the problem is, unless I climb that pole, I don't know what the transformer impedance is. So we're going to have to make some assumptions on this one. Hey, I'm up here. So these ones are a little different. Now, again, don't try this at home. I just happen to be up there because I know these aren't energized. But if you look at these transformers, it has 25 kVA. So three of them together make a bank in a delta Y configuration of 13,800 volts in this case to 480 volts, Y connected, so 480, 277. And this one's going to be solidly grounded. And I'm standing right up here next to the nameplate. So I'll show you a picture of the nameplate in the PowerPoint. But again, this is what you might see in front of like a strip mall. Now this is a 750 kVA pad mounted transformer. This thing's liquid filled or oil filled. And it's medium voltage on the input and 480, 277 on the output, for example, or it could be 208, 120 volt on the output. The interesting thing about this is without opening the doors, a lot of times you won't be able to see the nameplate. So sometimes they have written on the outside the kVA rating of these units as well from the utilities standpoint, so they know what size they are when they go to replace them if they fail. So this transformer is 5,000 kVA, but it also has a slash rating 6250. And that's because we have fans and radiators on the back to cool it down so the oil can move through those radiators and we get more kVA out of the transformer. That's going to come into our calculations for full load amps and also our fault current a little bit differently, so we have to think about that. This one has 34.5 kV in, 13.8 kV out.
Okay, so let's get into the fun stuff. Let's calculate the full load amps on the primary and secondary of a transformer. Here, I full load on the primary, I full load on the secondary, three-phase fault current, I fault three-phase here, and that's going to help us determine the wire sizes on the primary and secondary, as well as perhaps the breaker sizes here on the secondary and there on the primary. Now we're going to use the information from the transformer. So again, we're gathering information from the transformer's nameplate. Let's just use this as a very simple 1000 kVA, 13.8 kV primary to 480 volt secondary, impedance 5%. So we're going to go back to the equation that we started with and we talked about for three-phase power, which is kVA three-phase equals square root of 3, there's that square root of 3, kV line to line times I line. So if we solve for the current, I line equals kVA three-phase divided by square root of 3 divided by kV line to line. Then we just substitute in if we're on the primary or the secondary to calculate our current. So for example, current I full load on the primary is 1000 kVA divided by the square root of 3 divided by 13.8 kV. And so let's calculate that out. 1000 kVA divided by 1.73 divided by 13.8. And that works out to be about 42 amps. Okay. Now, if we want to look at the secondary current, I full load secondary, we would take 1000 kVA divided by the square root of 3 divided by 480, right? Well, here's what's going to get you in trouble. If you do that, 1000 divided by 1.73 divided by 480, your current is 1.2 amps. And if you have 1.2 amps on the secondary and 42 amps on the primary, you should know that something's wrong. And in fact, what you forgot is this is kV on the bottom, kV line to line on the bottom. So we have to do 0.48. So if we divide that or multiply that by 1000, we end up with the correct answer, which is 1204 amps. And one really cool thing about 480 volt systems is that if you take 1000 kVA, 1000, multiply it by 1.2, guess what? 1200 amps, 1204. So there's a good rule of thumb that basically says if you have full load amps on the secondary of if you have full load amps on a 480 volt system, it's about 1.2 times the kVA rating of the transformer. Now, let's take this to the next step, which is how do I calculate my fault current? So if I want to calculate my fault current, I three-phase fault, it's actually very simple. All we do is we take I three-phase full load amps secondary, divided by the impedance in per unit. And we'll talk about what that means. Basically, per unit at 5%, per unit is 0.05. So we take 1204 divided by 0.05, and we get 1204 divided by 0.05, and we get about 24,080 amps, or 24 kA. That's our fault current. This number, since the impedance is 5%, or 0.05, this number is 20 times the full load amps. Again, interesting things to think about. When you think about the impedance, 1 over 0.05 is about a ratio of 1 to 20, so the ratio of the full load amps to the fault current is 20 times. And that's how we're going to size our KA rating for our breakers. So those are just a few of the things that we want to think about. Now, on the next page, we're going to talk about the infinite bus, and why do we not calculate the fault current on the primary side? The reason we can't is we don't know what the impedance back here is. So let's talk a little bit about that. So what does an infinite bus mean? An infinite bus basically says that we have zero impedance all the way looking back to the source. And we know that's not exactly true. Of course it's not true. But if it's low enough, the calculations work out so that we can actually ignore the fault or ignore the impedance of the upstream transformers and cables and everything else, and just use the nearest upstream transformer as our main source impedance. That becomes especially important when you're doing things like fault calculations and even harmonic analysis, really, to be honest with you, for resonance and things like that. So if you can understand transformer impedances and you can calculate all that, then you can figure out, how that comes together. How much of a difference is it? It's usually less than 5%, and in fact, it actually errs on the conservative side. So if we ignore that impedance, what are we doing? We're making the impedance lower. If the impedance is lower, our fault current is going to be higher. So actually, it makes, for a better or a more conservative calculation. Now, what if our per unit voltage is not 480 or 13.8 kV, but maybe 5% high? Again, we have to think about that. So we may actually add in a little bit of fault current into our final calculations. Okay, so I showed you a few transformers earlier. Let's start to do some of those calculations that we talked about. So again, we're going to try to look for primary and secondary full load amps and secondary fault current. Now, here's the transformer, here's the inside of it, and typically you're not going to get to see it with a nameplate, with the cover off of it. So what we usually do is we walk up to the nameplate and we start to gather the information that's on the nameplate. What are we looking for? kVA rating. We're looking for primary voltage, secondary voltage. Sometimes we worry about the configuration if it's delta Y or delta delta, for example. But for these calculations that we're going to do, it honestly doesn't matter for that particular part. And then we also look for impedance, and that's the Z value that's on the transformer. Okay, so let's start in with the fun stuff with the actual transformers that we saw in the PQ lab here. This is one of my favorites, and you'll see why in a minute. It's 75 kVA, K13, which, by the way, K13, TP1, HMT, all kinds of strange transformer names that might come up. That's not going to affect your calculations for these things that we're seeing here. It actually does affect the impedance of the transformer, things like that, when it's put together. But in fact, whatever's on the nameplate is what you need. So as far as that goes, this information on the nameplate is all you need. 480 volt, 208, 120. What does that mean? It's 480 line to line delta on the primary, 208 line to line on the secondary, connected in a Y, so 120 line to neutral. And the impedance is 4.262%. So let's calculate I full load primary. All right, so we go back to our equation we had before. I full load primary is going to be, in this case again, 75 kVA. So it's kVA divided by the square root of 3 divided by kV. And again, we got to make sure we use 0.48 here. So we take 75 divided by 1.73 divided by 0.48. And we get 90 amps. Remember what I told you earlier? 75 times 1.2. Oops. Divided by 75 times 1.2 is 90 amps. So we end up with 90 amps, which is that 1.2 multiplier when you have a 480 volt system. Now here's the cool thing. If I want to calculate I full load secondary, I know it's 208 amps. How do I know that? Well, let's go ahead and multiply it out. 75 kVA divided by the square root of 3 divided by 0.208 volts, or kV, because it's 0.2, and we get 75 divided by 1.73 divided by 0.208, and that works out to be 208 amps. If you can remember that a 75 kVA 208 volt transformer gives you 208 amps, so 208 volts and 208 amps, what would be a 750 kVA transformer? Well, then it's 208 times 10, or 2080 amps. And again, that's just a side note. Again, rule of thumb, something to think about, something to remember in the back of your mind. And as I said in the previous page, what if it was 300 kVA? Well, if it was 300 kVA, it's 4 times this number. So an easy calculation for you to remember to do that. Now, so that's full load amps, primary and secondary. What if I want to calculate my fault current here? I fault. So then earlier I mentioned we just divide the full load amps by the impedance, but really what we're doing is we're calculating kVA short circuit. And kVA short circuit is kVA full load, which is our rating or rated, divided by the impedance in per unit. So in this case, it's 75 divided by 0.0462, which is 75 divided by 0.0462. That's 1623 kVA. And then that number, if we use our I fault three-phase, we're going to take our short circuit kVA, which is 1623 kVA, divide it by our square root of 3, and divide it by our 0.208 volts, which is 208, and we end up with about 4,511 amps of fault current. If I took my number here that was 208 amps, if I take 208 divide it by 0.0462, I end up with 4,502 amps, which is very close to that number. I just was off by basically the square root of 3 factor that works out in there. But anyway, this number, our full load amps and our fault kVA are important. And so you can see that we're using the same equation. We're using that same equation, which is kVA equals square root of 3 kV line to line times I line. And if that kVA is our fault kVA, which is what we used here, we can then calculate the fault current here. So the equations are all the same. It's either kVA full load or rated, or kVA fault. And the way you get kVA fault is divided by the impedance. But again, if you can remember that 208 volt and 208 amps, that's going to come in really handy. Now this transformer is a little bit unique. This is called an isolation transformer. And again, isolation transformers might be used in front of a motor drive as is shown here. The interesting thing about isolation is, again, it goes 480 in or 460 in this case and 460 out. Okay, for the next transformer, we have this unique isolation transformer. And again, it's 550 kVA, 460 volt rated in, 460 volt rated out, 500 or 5.12% impedance. Now, we're probably going to apply this on a 480 volt system. So the bus voltage here is 480 volt, and the bus voltage here is 480 volt line to line. But how are we going to calculate the full load amps on the primary and secondary and calculate our fault current? So again, we'll start with our same equation we've been using the whole time here, which we're going to do I full load primary, and in this case it's going to be the same as secondary, coincidentally because the voltage is the same, is going to be 550 kVA divided by square root of 3 kV line to line. Now the tricky part is, do we use the rated value or do we use the actual applied voltage? And what I'm going to tell you here is, let's do it both ways. Let's do 460, and then we're going to do the same thing, 550 kVA divided by square root of 3.48, and let's just see what the difference is there. So 550 divided by 1.73 divided by 0.460. Now that gives us our 691 amps. If we do the same thing, 550 divided by square root of 3 divided by 480, we get 662 amps. The windings and the actual transformer are designed to handle 691 amps, but what you have to remember is kVA is a capacity thing. It's volts and amps together. So if we run at a lower voltage, we could go up to that amp capacity rating. If we run at a higher voltage, we're likely going to only want to put up to that many amps through it. Otherwise, we're going to exceed the kVA rating of the transformer. So that's why these two numbers are important to understand. Most of the times, you'll see motors rated at 460. You'll see transformers rated at 460. A lot of times that's because they're down in the system where you expect the voltage to run somewhere near that level. And so to get the full load capacity out of them, you can use that 460 volt level. So anyway, again, sizing the breaker here, we might size it for 660. Well, it's not going to be exactly that. It's going to be something less or a factor of that, even a little bit more, depending on how our protection scheme is done. But we're going to typically base it on that because we know we're applying it at 480 volts. Now the fault current, I'm going to use that I fault I'm going to use the short circuit kVA for this one. And the reason I'm going to use the short circuit kVA is because that's based on the rating. So, and then the kV line, we're going to divide that by the impedance. So we're going to do 550 divided by the square root of 3 divided by 0.46. And then that's our short circuit kVA divided by our impedance, which is 0.0512. So we get 550 divided by that, that's going to be that number, 691, divided by 0.0512. And that's going to work out to be 13,496 amps. That's our fault current. And honestly, again, these are estimated values. So let's talk about that for a minute. If we have an estimated value of 13,496 amps, is it going to be that? No, absolutely not. It's going to be probably less than that. Why is it going to be less? Because remember, we ignored our primary impedance of our source above that. And a lot of times in this case, especially where you use an isolation transformer, the transformer upstream of this might not be very small or very big. In fact, it might be closer to the range of this transformer. So we do have to take that into account sometimes in a more formal study. But again, it's going to knock that number down. Also, if we have motor contribution here, that motor contribution could increase the fault current for a short period of time during fault conditions. So again, these numbers are estimates. If that number was 13,500 amps and you were putting 35 kA breakers in on this system, it's not going to matter. It's so different that it doesn't matter. If this number was 34,000 amps and we weren't exactly sure what the impedance up here was going to do and the motor contribution was going to do, I would be much more concerned. So again, using these estimated calculations, we can go through that and figure it out. Okay, now moving on to a different type of transformer. These are pole mounted transformers, and this is actually the kind of transformer that's going to be out in front of your house, for example. You either have this type of transformer or you have one that's pad mounted, but in the case of the size, it's usually 10 kVA, 25 kVA, and that's what we see on this one. 10 kVA, that's the number that's written on the side of the transformer. Okay, now this is a fun one because this is what's outside your house. And you want to think a little bit about what's the full load amps on the primary and secondary on this transformer. I didn't draw the secondary here because I want to show you something. This is 13.8, typically line to line, or it could be line to neutral, which is this number divided by the square root of 3. And so if we knew the primary voltage, let's say 13.8 kV, and we divide by the square root of 3, we would get 13.8 divided by 1.73, 7.97. So that would be our kV on the primary side. Okay, but the way you can tell that is if you look at the transformer, and the transformer has two bushings that are about the same size. Typically, they feed them line to line. you'll see your secondary bushings coming out of the secondary here, and the 240 volt and the center tap neutral, grounded neutral is coming off there. If there's only one tall bushing and one short bushing, then a lot of times it's lined to neutral. They do that because the cost of the bushing obviously adds to the many, many, many transformers that are out there. So sometimes they apply them at line to neutral rating, or in this case, line to ground, and sometimes apply it at line to line. But we're going to just say it's line to line for this one. The secondary of the transformer looks like this. This two windings coming off of there are 120 volt to a grounded neutral. So the neutral is grounded. It's brought into your home. And so it's 120 volt here, 120 volt here, and then 240 volt from here to here. So what are we going to calculate? The breaker that's in your home typically is a two-pole breaker that's connected on that 240 volt line. So we're going to calculate based on the 240 volt. So instead of using that kVA three-phase is equal to square root of 3 kV line to line times I line, we're just going to say kVA equals kV times current. In this case, we know the kVA, which is written on the side of the transformer, is 10 kVA. And then the voltage is either going to be 13.8, we said, on the primary. So that'll give us our I primary, full load. Or, and so let's just calculate that out. So we'd have 10 kVA. So I equals 10 divided by, I want to use my square root of 3 in there. I divided by voltage, so 13.8. So 10 divided by 13.8. And really right away we can see that's less than 1 amp. So 0.725 amps. So that's what's kind of cool if you think about it. They could use almost like an Ethernet cable to feed your house. It's very, very low gauge wire, but that's why they can use like a 10 or 12 gauge wire uninsulated in the air, just feeding the primary. And you're going to see that that wire is small. It doesn't even need to be as big as it is because you have less than an amp on the primary. The other part about this that's cool is if you look at the secondary, secondary full load, we have 10 kVA divided by 240, so 10 divided by 0.24, and we get about 42 amps, 41.67 amps. So for obvious reasons, then we put 200 amp panels in, or we put multiple 200 amp panels in our house, right? What's cool about this, when you think about it, our panel in our house is 200 amp, but we can only supply 41 amps or 42 amps from the utility transformer based on its capacity. But the utilities actually will push these transformers up even more, and they'll let you draw through maybe almost 2 times the normal kVA because they'll just let them blow off the poles. But the reality of it is you're never going to approach the 200 amp panel that's in your house. So why do we put 200 amp services in? Well, we don't know. If they have a 10 kVA transformer, they may upgrade that to a 25 kVA transformer or maybe 50 kVA. So we don't know. And so the capacity of the service coming into your house is what really dictates your breaker, and not necessarily the full load amps in this case. Now, as far as the fault current, let's just take that number, 42 amps, and divide that by our impedance. What is our impedance for this kind of transformer? I said it earlier, it's going to be between 2 and 3%. So let's just use 0.0. I think the one we showed was 2.4%. So take that number divided by 0.024, and we get 1736 amps. Typically in our homes, we're using 10 kA breakers, so this is well within that range. Now let's take a look at this transformer, or this set of transformers. These are 3-pole mounted transformers. Again, oil filled or liquid filled. These ones happen to have FR3 in them. 25 kVA, that's what the 25 is on there. And actually, if you get up close, and again, if I, up earlier, I was up showing you from the bridge there. If I looked at that nameplate, I could actually see the nameplate and the impedance of this transformer. In this case, it's 2.4%. What's interesting about pole-mounted transformers is they do have a lower impedance. So we made an assumption earlier, if you didn't know the transformer impedance, you could say 5.75%. But in this case, if you don't know the impedance of a pole-mounted transformer and you guess that high, guess what you're going to do? You're going to influence your fault current calculation. So it's important that you don't overestimate the impedance of a pole-top transformer. And so if I don't know the value, I might even guess 2% for that one. So 2 to 3% is a typical number. Okay, now that we're getting pretty comfortable with these calculations, we're going to throw another little wrench in the plans. We're going to say there's 3 single-phase transformers pole-mounted, and those transformers are connected in delta Y, as shown here, delta Y. So this winding corresponds to that one, this one to this one, and this one to that one. Each winding, each transformer is rated 13.8 kV line to line, 277 volt line to neutral. So here's our neutral point on the secondary of the transformers. 480 volt line to line on the secondary. So our difference in our calculation really is we're going to take this 3 times 25 kVA and make it a 75 kVA transformer. There's our square root of 3 and 13.8 kV. That works out to be about 3 amps. So again, even though the wire size could be very, very small, in this case, we only need about 3 amps on the secondary, on the primary. And on the secondary, again, we already know what that's going to be. It's going to be 75 times 1.2, or about 90 amps. So again, we're starting to become more and more comfortable with that. Why is that? Because we're a 480 volt system. Our multiplier on our kVA is about 1.2, so we're at about 90 amps. Okay, now why am I using 13.8 kV? I could use 12.47 kV for medium voltage. I could use 13.2 kV. I could use 13.8. I may even go as high as 34.5 kV for medium voltage, and I might go as low as maybe 4160 volts or 4.16 kV. But anyway, or even 2.4 kV. But the point is, I'm trying to be consistent, so I'm using the 13.8 for this calculation. So again, you can see what our load currents are going to be primary and secondary. Now let's calculate our fault current. So I fault 3-phase on the secondary is going to be 90 amps divided by our impedance. And again, the impedance for these guys is typically pretty small. So we're going to use, the number on the nameplate in this one, 0.24 per unit, or 2.4%, and that works out to 3750 amps of fault current. So this transformer is 750 kVA, delta Y 13.8 kV to 480 volt. Now, what's unique about these pad-mounted transformers that you might find out in front of a building just like the one I'm in today here is that you can't really tell a lot of times what size they are, and you don't usually get to access the nameplate because the nameplate might be behind one of those 2 doors. So you might have to rely on numbers that are on the outside of the transformer, but most likely you want to talk to the utility company and get that information from them, especially as it relates to impedance and kVA size. So if you have a pad-mounted transformer like this one, how do we know what the ratings are for it? As I mentioned, you can't get inside the door. So a lot of times we'll talk to the utility company, and let's say we determine that the kVA rating, either with some numbers written on the transformer, was 750 kVA, and we couldn't get a hold of the utility company, so what are we going to guess? Well, honestly, it's difficult to guess at transformer impedances, but in many cases, if we don't know the answer, a traditional impedance to use is 5.75%. I will tell you, though, that depending on the size of the transformer, this is not a great number for much larger transformers. And again, we mentioned pole-mounted transformers is not appropriate. So for kind of medium size and smaller dry type transformers, if you don't know, you can use that number, but again, using a bigger number gives you less fault current. So we want to be careful we're not overestimating impedance. For this liquid filled transformer, we're going to use 5.75. But anyway, so let's say we figure out I full load on the primary is about 31.4 amps. And I full load on the secondary, and I know what you're going to do. You're going to take that 750 and do what? You're going to take that 750 and say 750 times 1.2. You come up with 900 amps, right? So now that you came up with 900 amps and we did the calculation to calculate the primary amps, it's kind of interesting. If you take the wire that would be used for the primary and secondary and look at it, I'm going to try to hold this at the right angle here, but you can see that you'd need 3 of these conductors on my right hand compared to the 1 conductor on my left hand. This would be your primary voltage wire and your secondary voltage wire. And so as you can imagine, why do we use transformers? Because small currents, a little bit of copper. Large currents, much copper, and anymore, it's super expensive to do that. So let's calculate our fault current, divide that number by 0.0575, and we're at about 15,652 amps of fault current. So finally, we'll talk about this transformer. This is a substation transformer, and what you see on this one is a couple interesting things. One is if you look in the back side of it, it has those radiators and fans. What that allows you to do is get multiple ratings. In this case, 2 ratings. It's 5,000 kVA base rating, and then it has a 6250 rating with the fans and the coolant going through the system. So what that allows you to do is run more power through it in terms of kVA. That also is going to come into play when we talk about our calculations for this transformer. This one in particular is 34.5 kV input and 13.8 kV output. Okay, now, so for this last transformer, this one adds a little bit more complication in a different regard, and that is that it has a slash rating. It has 2 ratings. It's 5 MVA, but it's also 6250 kVA. How do we determine what the full load amps are on the primary and secondary and the fault current? How do we determine that if we have 2 different ratings for kVA? Which kVA do we use for which? If you think about it, the kVA rating, the slash rating, really indicates that if we have cooling, we can run up to that level, the 6250. So when we calculate our primary and secondary full load amps, we want to use 6250 kVA. That means that's the most we can get out of that transformer. So our current has to be rated based on that. So if we take 6250 divided by 34.5 divided by the square root of 3, we end up with 104 amps, about 105 amps, 104.7 amps. If we look at our secondary, we take 6250 divided by square root of 3 divided by 13.8 kV, we end up with 261.8 amps. So that's our secondary current and our primary current. Now, in a normal situation, if we were just calculating the fault current here, I fault, we would just say, take this number divided by the impedance, which we know is 6.1%. However, this 6.1% is not based on this 6250. This 6.1% is based on the base rating, because there may be 2 or 3 ratings for kVA. This 6.1% is only based on this value. So we need to go back to our short circuit kVA rating, which is going to be 5,000 divided by square root of 3 divided by 13.8 kV, and then divide that by the impedance, which is 0.61. And that number would be 5,000 divided by 1.73 divided by 13.8. So that number is 209 instead of 261. Then we divide that by 0.061. Otherwise, our fault current would be higher, 3433. Otherwise, our fault current would be higher than it would be if we use the other number. It would be higher than it would be in reality based on the impedance of that transformer. And again, we're starting to get into that situation where we may want to look at what the actual source impedance above there is. So those are the key things here. 6250 is the most kVA we can get through it. So the most kVA means the most, in other words, in order to use the full capacity, we want to base our primary current based on that 6250. If you base it on this one, you're just limiting the capacity of the transformer artificially by putting a breaker or something ahead of it and limiting the capacity of the load. And then for the fault current, we used 5,000, or we used the base rating in the base impedance. So a lot of questions come in when we're doing this class in person about the impedance of the transformers being the same and the kVA being different and how that affects your system and really what that means. So if you think about it from a very simple example, a 30 kVA transformer versus a 3 MVA transformer, which one of them is going to provide more fault current? And I think we would all come to the conclusion that the 3 MVA transformer would provide more fault current at the same voltage level. What happens if you have two transformers in series? How do you add them together? And so let me show you that as a quick calculation. Okay, now here's a situation that you also have to understand. What if I have two transformers in series and the ratio of those transformer kVAs is not 10 to 1 as we've been assuming? So we can just say it's an infinite bus above the downstream transformer. In this case, these two transformers are actually relatively similar in size. We want to add them in series to create that series impedance so that we can figure out our total fault current at this point on the system. Now, the nice thing of it is if we calculate the fault current here, the only thing we need to know is which kVA to use, and we're going to use kVA base, one or the other of those kVAs, and then we're going to use a Z per unit total, which is the series sum of those impedances. But we can't just take 5%, 5%, and call it 10%. We have to combine those on a common base. So what I like to think of is if you take this transformer and this transformer and you say which one delivers more fault current, and I would say the 1000 kVA delivers more fault current. So if I put those side by side, this one has a higher impedance. The 500 kVA has a higher actual impedance in ohms compared to this one. So if I want to take my Z base or my kVA base, and make it 1000, then my Z for this one, Z1 is 5%, and then my Z for this one is going to be bigger or smaller, and as we said, it's more impedance at that base. So we're actually going to say Z2 is the new base, which is 1000, divided by the rated, which is 500, times Z here, so 5%. So that gives us a total impedance of 10% for that one. So Z1 plus Z2 in that case is 5 plus 10, and I would end up with kVA base 1000 divided by the square root of 3 divided by 480, and I think we know what that number is by now, which is 1200, and then we divide it by our total impedance, which is 0.15, or 5% plus 10%. So we take 1200 divided by 0.15, 1200 divided by 0.15, and we end up with about 8,000 amps of fault current. Now, what I'm going to do is I'm going to show you that it would be the same if we went the other way. Let's say we take our Z base is kVA base is 500 kVA. So Z1, again, delivers less impedance at that 500 kVA base. So it would be Z1 would be 500 divided by 1000 times 5%. We end up with 2.5%. Z2 at 500 is going to be still 5%. So Z2 is 5%. And then we add those two together, and we end up with, basically, let's do it here, 500 divided by square root of 3, 480, divided by 0.075, which is 0.02, or 0.025 plus 0.05, and we'll get 500 divided by 1.73 divided by 0.48, which is half of that 1200 that we should get, right? And then divide that by 0.075, and we get 8,000. And again, it's a little bit of rounding error for my square root of 3, but these two numbers are the same. So again, we can calculate that fault current either way, but we do need to combine those bases to make sure that the transformer impedances are based on the same thing. Okay, now that you're all formal experts on calculations for anything transformer related, right? You can do the full load amps and the fault current calculations. Let's talk a little bit about motor starting and what's important for that. We're going to do a couple quick hand calculations, and then we'll kind of figure out where those thresholds of concern are, wherever we're going to have voltage drop according to motor inrush. And then we'll talk a little bit about motor starting and basically using computer simulations for that analysis. And then finally, really, we're going to talk about how that might or might not affect demand charges. So now we're going to do a simple hand calculation based on motor starting to calculate the voltage drop associated with the inrush current of a motor. And as we know, the motor inrush current is typically considered 6 times full load amps. So that current has to flow down through the transformer into the motor. And so when we talk about a motor, we have I full load amps. We can calculate that. But the inrush current is 6 times I full load amps equals inrush. Now, what's interesting about that is horsepower is just about equal to kVA. And if you do the calculation and take out the efficiency and the power factor and everything, you end up finding out that horsepower is about equal to kVA. So we have about 30 kVA of normal load, kVA. As we look at inrush, then our inrush is 6 times our normal kVA, which is 30. So 6 times 30 was 180 kVA inrush. So if we just take that number, that inrush kVA, and look at the ratio of that inrush kVA versus this transformer size, so basically we take kVA inrush divided by kVA of the transformer and multiply it by %Z, we get 180 divided by 550 times 5.12%, and here's what we get: 180 divided by 550 times 5.12%, and that ends up being 1.67% voltage drop. So again, in summary, what we saw there was that the motor is going to give us about 6 times inrush current. So once we create 600% full load amps, basically for that motor, we had about 180 kVA of inrush kVA, and then we basically ended up with about 1.67% drop. So really, for that percent drop, we don't really need or require formal analysis, and we should be good in this situation. So then if we repeat that, 75 horsepower, 75 kVA times 6 gives us about 450 kVA of inrush divided by the transformer kVA times the impedance of the transformer, which gives us about 4.1% voltage drop. So again, in this case, we have a little bit more inrush current because the motor's bigger. We have about 450 kVA worth of inrush kVA. Compare that to our 550 kVA size of our transformer. You ratio that and look at the impedance, and we get about 4.1% drop. Now, again, that doesn't really require formal analysis, but we will see that in terms of light flicker. And so again, as you see, if the motor was starting many times a day, you might get more of an inrush effect in terms of people noticing and maybe problems associated with that. And then looking at it for 300 horsepower motor, we have 300 times 6 times inrush to give us 1800 kVA divided by 550. So again, that number is going to be bigger than the impedance. In fact, it's 16.5%. Now, finally, for this one, what you notice that's interesting about this is our inrush kVA, our 1800 kVA, is actually bigger than the transformer by a good bit, about 3 times or more than 3 times. So we're seeing about 16.5% voltage drop, as we mentioned. So if we do that, what's going to happen is we are going to see a significant notice on light flicker, but also we may actually have equipment dropout. So this case, we probably do want to do a formal calculation with some sort of a computer simulation to make sure that, again, these hand calculations are very rough, but to make some additional calculations to see what the actual drop is, and really, honestly, how long it's going to last in terms of the motor starting and so forth. Now, one of the questions I get quite a bit of is, you get these peak and rushes of different things throughout the day. Is motor starting going to affect my demand charge? No, really, it's really more about understanding what demand charge is. Demand charge is the 15-minute window that the utilities look at and see what your maximum demand is for the month in terms of kilowatts or megawatts. And the reason that they need to have that number is so that they can supply a customer, in the worst case scenario, with the capacity of their system. And especially if all the other customers have, a maximum capacity at a certain time, the pipe, the actual wires, the transformers, and everything behind it, the system has to be able to withstand that. What's interesting about that is a lot of people assume that when you start a motor, you get this big inrush current, you're going to affect that demand, and that's not really true. The fact of the matter is that the inrush for a motor is very short in terms of seconds. Even for big motors, it's 5 to 10 seconds. And so over that 15-minute window, it's very minimal. And the other part of it is that that inrush current is actually reactive current for the most part. So even though it seems like it would be a big deal, it really doesn't affect the demand. And that's very important to know as you think about promising a customer whether or not they're going to save money by putting in a soft start, for example, because it's not going to change your demand. It will affect the motor inrush. It'll save the motor from being potentially damaged for doing that over and over again, and it also save the voltage drop. That's very important from these calculations, but it's not going to affect the demand. Okay, now let's switch gears again. So here's the power triangle. We're going to talk about power factor correction for a minute, and we'll do a couple quick calculations here around that. But for example, when we look at the power triangle, we look at the real power on the x-axis, reactive power on the y-axis, and on this hypotenuse here, this is the apparent power, or kVA. So how do we calculate that? We take the power factor, which is the difference between kilowatts divided by kVA, or the ratio of kilowatts divided by kVA in this case is 0.8. Okay, for the last example, then we're going to give you an example of power factor correction and how would you apply capacitors to correct for a power factor so that you could add more load. In this case, we have a transformer that's 500 kVA rated, 500 kVA rated, and it has a 500 kVA load flowing through it to this motor, 500 horsepower, 0.8 power factor. So at 0.8 power factor, our kilowatts are 400, our kVAR are 300, and our kVA again is 500. So that's what's flowing through the transformer right now. We want to apply a capacitor to relieve some of the capacity of that transformer so that I can add another load over here. And I can put some other load, whether it's resistive or reactive or a combination of loads. So let's say the target power factor, power factor is 0.95. How do I get there? So my target power factor is 0.95. My actual new kVA then, kVA new, would be my existing kilowatts, which is 400, because my kilowatts aren't going to change. Those have to still come from the utility, divided by my target power factor, which is 0.95. So if I do that, I take 400 divided by 0.95 and end up with 421 kVA. That's going to be my new kVA, and that's what I'm going to shoot for by adding a capacitor in. So how do I size that capacitor? Well, first I have to figure out how many kVAR are left if I do that. And I know my new kVA is that, so my kVAR would then be square root of 421 squared minus 400 squared, which is my kilowatts. So 421 squared minus 400 squared, take the square root of that, and I'm left with 131 kVAR. Now what's important to know about that is that's what's going to be flowing up through here, 131, if we had if we had a 0.95 power factor. I still have 400 kilowatts flowing through there. What I have to do though is when I apply a capacitor here, I have to negate what's already there, which is 300. I have to get it down to 131. So that means I have to add 169 kVAR capacitor. Well, we know we're not going to buy that. So because it's just not a standard size. So what we're going to have to buy is a 150 maybe or a 200 kVAR. But since we know our target power factor is 0.95, I can't go lower than the number I came up with. So I'm going to have to go higher. And so what I'm going to do is I'm going to apply a 200 kVAR capacitor here. 200 kVAR to negate that. So that means I'm putting a 200 kVAR capacitor here. And what am I going to end up with? Well, if I put a 200 kVAR capacitor in there, now my new kVA is kilowatt squared, so 400 squared, plus 300 minus the 200 that I'm putting in there, so plus 100 squared. My new kVA, 400 squared, plus 100 squared, and then take the square root of that, 412 kVA. And so now my new power factor, new, is not 0.95, it's actually better than that. It's 400 divided by 412. 400 divided by 412. And my new power factor is 0.97. So what that means is I now have on my transformer up here, I have 400 kilowatts still flowing. I have 100 kVAR flowing, and my new power factor is 0.97. And that's how I do my power factor correction, by adding a 200 kVAR capacitor to an existing load. That frees up some capacity of the transformer in terms of 500 kVA. Now I can add another, roughly 88 kVA of load without any concern. Okay, so we went through all these calculations. We showed you some examples of rules of thumb. What are some of the key ones that we pointed out during the actual examples? For 480 volt systems, basically the amps versus kVA is about a 1.2 factor. So if I'm at 75 kVA, I'm about 90 amps. And that's a really important and easy one to kind of remember. So if I'm at 750 kVA, I'm at 900 amps. Those are things that you're going to want to keep in the back of your mind. So when the person next to you has that kind of quick calculation in the back of their pocket, that's where they're getting that. 208 volts, 208 amps at 75 kVA, and you can scale it up and down from there. So if you're at 300 kVA, you can multiply by a factor of 4, and so forth. And I think that's a really important one to remember. Again, you can impress your friends and your family with that one for sure. Horsepower is about equal to kVA. So if you're doing motor calculations, you can put in the efficiency and you can put in the power factor and all that. At the end of the day, it's just about equal to kVA. So I think if you make those calculations, you're not going to be off by much. And if you are, again, marginal on anything, and again, this goes with any of these calculations, if you're marginal, you need to go back and kind of fine tune it anyway. And then normally assume an infinite bus if the transformer ratio is 10 to 1, kVA wise. So if I have a 1000 kVA transformer and I'm fed by a 10 MVA substation upstream or even bigger, I usually don't have to worry about anything in terms of my fault calculations and using that impedance to really affect things. I had a lot of fun doing this session, And I think it's important that you kind of understand some of these basic calculations and things like that, so you can do the back of the envelope, napkin, or pizza box calculations as well. So now you know why it's important to know these basic equations. And I think as a consultant, it's really important to understand where they come from and how you can get to these basic calculations. The second part is really knowing that the person next to you, through all that experience, this is the knowledge they've gained, and they've been using these kind of calculations for a long time. Power systems, if you understand those kind of key equations, you can get through a lot of the calculations that you need. And now you have all the tools to solve your basic power problems. So I hope you enjoyed it. Thank you very much for joining us.